Hello, this lesson is going to explain the most relevant information regarding the test methods and standards of fiber reinforced concrete. First of all, we are going to explain how are the fibers classified in some of the most important regulations. As can be seen in the slide, in this course we are going to consider three recommendations. First of all, the European standard EN 14889. This regulation considers two types of fibers, steel fibers and polymeric fibers. Secondly, the Spanish code for structural concrete, which is commonly known as EHE 08. This code does not take into account the material of the fibers, but if the fibers are structural or not. In addition, it establishes some advices related with the use of glass fiber reinforced cement. And finally, the American Concrete Institute divides the fibers into four classes: steel fibers, glass fibers, synthetic fibers, and natural fibers. In this course, we will focus on the European standard that divides the fibers between steel fibers and polymeric fibers. The European standard EN 14889 that was approved in 2008 establishes the characteristics that are relevant to classify the fibers that are used in concrete. The main division is stated based on the material of the fibers. Consequently, this standard considers the steel fibers and the polymeric fibers. Among the steel fibers, all types of steel fibers are considered. There can be modification of the types of the steel ranging from carbon steel to stainless and galvanized steel, or even the process used to obtain the fibers. They can be obtained from wires, sheets, blocks, or some others. In the case of polymeric fibers, almost all of them are manufactured using plastic that are part of the polyolefin family. In this category, polypropylene fibers are included. The polymeric fibers are secondly divided regarding their equivalent diameter. Class 2 are those fibers that are considered non-structural due to their reduced size, and they can be either fibrillated or monofilament. Class 2 are those considered macrofibers, and their equivalent diameter is greater than 0.3 millimeters. In this course, the types of fibers that are relevant are steel fibers and polymeric fibers. The most important mechanical property of concrete is compressive strength. This property has a remarkable relevance even in the case of fibre reinforced concrete. Similarly, the indirect tensile strength of FRC is assessed by means of the Brazilian test. However, in none of these two tests, the contribution of the fibers added to the concrete have a remarkable influence. In order to evaluate their influence, it will be necessary to perform uniaxial tests. Such test has great advantages, like its simple interpretation and its pure stress state. However, the uniaxial tests have some disadvantages that are difficult to overcome. The test setup is quite expensive, and the preparation of the sample is both time and monetary costly. In addition, this type of test is difficult to perform because the results that are usually obtained are not satisfactory due to the breakage of the samples in the whereabouts of the jaws. Finally, the technicians that should carry out the test have to be highly trained. Due to all these reasons, the test that is commonly performed in order to study the influence of the fibers in the concrete is the three-point bending test performed in notch samples. Such type of test is carried out to determine if the steel fibers or the polymeric macrofibers can be considered in the structural design of the concrete element. The European recommendation that establishes the procedure is the recommendation EN 14651 that was approved in 2008. This test is similar to the test proposed by the Relem Association test method. This method is focused on assessing the improvement of the concrete mechanical properties that were achieved by adding randomly distributed fibers in concrete. In order to do so, the test method employs prismatic samples with a square section of 150 millimeters of length, and the total length of the sample is 600 millimeters. The sample is notched in its central section, leaving a ligament of 125 millimeters that is subjected to a three-point bending test. The mechanical behavior of the material is derived from the data recorded during the test. The data has to be acquired using one craft mouth, opening displacement gauge, placing the lips of the notch. In the size of the sample, in its central section, there are two linear variable differential transducers. The loading signal that is seen in the sketch of the slide is connected to the machine actuator with a load cell. In the slide, a real image of the EN 14651 test can be seen. It has to be highlighted that the sample is supported by two cylinders that have a free rotation in all the directions of the space. In addition, in the image it can be seen the CMOD gauge that controls the test by fixing the opening rate of the gauge. In the detailed image, it's easy to perceive that the CMOD is placed in the sample using two steel blades glued to the sample surface. To obtain the energy that the sample absorbs during the test, it is necessary to acquire the displacement of the loading cylinder. Such displacement is registered by two LVDTs placed in the sides of the sample, as can be seen in the image. In the plot graph, the typical behavior of a conventional plain concrete can be seen. It's obvious that the linear loading branch is abruptly finished when reaching the peak load. After this load, the loading continues monotonically after having a quasi-exponential shape. In the case of a steel fiber reinforced concrete, the test behaves similarly to the plain concrete test until the unloading branch and where a reloading part starts. This reloading part ends at a greater deflection and the final unloading branch starts. In the case of macropolymeric structural fibers, a similar behavior is registered. However, the reloading takes place for a greater deflection, and the post-peak maximum load takes also place for greater deflections. After knowing the typical behavior of the two types of FRC, the question is, what characteristics should a FRC have in order to take into account the contribution of the fibers in the structural design? These characteristics depend on the recommendation, but for the Model Code 2010 and the Spanish Structural Concrete Code, such recommendations are the same. Given a curve that shows the strength crack opening of a certain FRC, both regulations establish that the contribution of the fibers can be taken into account if two conditions are met. Firstly, for a crack opening of 0.5 mm, the stress should be greater than 40% of the stress that the material can bear at the peak load. Secondly, for a crack opening of 2.5 mm, the stress that the material can bear should be greater than 20% of the stress at the peak load. Whereas the first condition avoids an excessive brittleness of the material, the second condition corresponds to the ultimate stress state of the concrete element. In the case of other regulations, such as the EN 14889, this regulation establishes a minimum stress of 1.5 megapascals at 0.5 millimeters of crack opening. In order to change the loads into the strengths, the formula that can be seen in the slide should be used. Thanks for your attention.